Today's topic is going to be mathematically intensive. So we're going to use integration method to determine the shear force and bending moment equations. And I would like you to see what is the advantages of using integration method. It's a very powerful method. And then we're going to look at the elastic curve method, a different technique that I'm going to show you to determine the slope and deflection of the structure. And this week, I did not post any quizzes yet. It's my fault. Okay, so what I'm going to do is at the end of Friday, or before the end of Friday, you will get two quizzes. Okay, or two quizzes that are intertwined together. Okay, so you need to know what you learned last week and this week to do those two quizzes. Again, my apologies because I was busy looking at the marking scheme and seeing where most of you don't understand or make mistake in term test 2. Right. So I'm going to we're going to go into integration method. Okay, we're going to go into integration method. So the integration method is for beams. Okay, so we're going to have a beam, a simply supported beam. So you have a pin on one side and a roller on the other side, right? And this is my point A, and this is my point B. So the thing about the integration method is, what is it actually used for? Now, let's say your load distribution on your beam now is not evenly distributed or graded, but rather is a function distributed load. So a function means like this. Okay, so this is your distributed load now. So with a distributed load, the problem with this now, okay, so this is our distributed load equation, omega as a function of what? As a function of x now, okay? So the problem with a distributed load like this is, what is the problem? It's difficult to find the equivalent load
Eugene, you're muted. Eugene?
Can you hear me now?
Yeah.
Okay. So
it might be Razor Cinepause.
Say it again.
It might be Razor Cinepause that's doing it.
Who?
It's the Razor software.
Oh.
For your headset.
Okay. That's weird. Okay, but anyway, so it's difficult to find the equivalent load. Now let me phone again. Hold on. Sorry about this. You can hear me, I suppose, yeah? Okay. So it's difficult to find the equivalent load and the position where the equivalent load is acting on. Okay, it's difficult. So what do I mean difficult? So we know when it's an evenly distributed load, right? When it's an evenly distributed load, so this is our evenly distributed load, right? To find so this is L and this is omega. To find the the equivalent load is straightforward. You guys know by now, right? So this is my point A. This is my point B. This is my point A. This is my point B. Right? So what we have is we know that the equivalent load is omega L, right? And the position of the equivalent load is equal to L divided by 2, right? This is straightforward. Then if we have a gradient distributed load, so if we have a gradient distributed load now, right? So this is omega. This is across distance L again. Let me be more specific. So again, one point is pin, one point is on a roller. Now you have a distance L. And then the equivalent load now, as you can see, this is point A, this is point B. The equivalent load will be over here and will be equal to omega L divided by 2. And the position of the distance or the position of the equivalent load over here is L over 3. Right? So this is the position. So this is straightforward, right? This is really, really straightforward. Very easy to find. But what if now we have a distribution that look like this? Okay, what if now we have a so when you have a distribution that look like this, it's no more so straightforward anymore, is it? Right? It's not like, hey, it's so easy to find the distributed load. No, it's not no more so straightforward anymore. So when that's the case, we have to use integration method. Okay, we have to capitalize on the integration method. So in the integration method, we have to find the relationship with dv over dx. Okay, so now we have dv over dx is equal to minus omega as a function of x. Okay, so this is the first step that we have to capitalize on. So we have dv over dx is equal to the negative of the distributed load. Now I'm not going to derive this. Deriving this will take me a good half an hour. Okay, so I want you to apply this function now. Okay, where dv over dx is equal to minus omega x, where omega x is the equation of the distributed load.
Eugene, would we have to use integration by parts at all during this?
It's going to be a very easy integration. Don't worry.
Okay.
Okay, it's not the integration that you learn in math. Okay, my integration is Mickey Mouse integration. I'll tell you that. But you need to know your fundamentals in integration. Okay. So if I'm going to pick 2 points now. So this is our point C. And over here, this is our point D. Again, the basic principle is still the same. The datum is still on the what? It's on the left-hand side. So the distance from here to here is x at point C. And then the distance from here to here is x at point D, right? So we want to find the shear force. Okay, we want to find or not find, just between point C to point D. Right, between point C to point D. So what we have is we're going to integrate dv, right? So when we integrate vd, we want to find v at point C and v at point D, right? And then this will be equal to x at, sorry, the other way, I do apologize. V C is below the shear force at point C, the shear force at point D. So this will be x d.
Eugene, your surface froze. it's not writing. Oh, now
okay.
it's there. It lags.
Yeah. And this is, yeah, I realized that also because I'm monitoring. I get that. Okay. So this is XC. Okay. And then we have minus omega X dx. Okay. So this is the expression that we have. So one thing I want you to observe now, this is where it's important. So when you integrate, what you have is this. Okay. So V at point D minus by V at point C is equal to, you integrate X at point D, distance at point C, minus omega X dx. So I want you to observe the left hand side is V, the shear force at point D, minus by the shear force at point C. Okay. So what is very interesting about this is you don't need to find the reaction force at point A and point B. I repeat again, you will not need to find the reaction force at point A and point B. Now, there's a bit of a lag. I will try to make sure that when I show a diagram, the lag will not affect you. Okay, right. So now that is the expression for the shear force. Okay, then the next thing that we have, right, is dm by dx. So what is the same over here is this is also equal to dm over dx. Okay. So dm over dx, the next expression is equal to v as the function of x. Okay. So this is another expression for the integration method that's rather critical. So when you differentiate moment as a function of x, right, is equal to your shear force, right? So then it's now between point C to point D again. Right, between point C to point D, then again you have moment at point D minus by moment at point C. This will be equal to distance of point D over distance of point C, and V as a function of x now, and now this is dx. Okay. So again, what I want you to take note on the left hand side is moment at point D minus moment at point C is equal to the integration of the shear force equation, and then the limits is between the distance of x at point C and distance of x d. Okay, so this is how the integration method works. So mathematically, this is how it works. Now, let's do an example. Okay, let's do an example to see how this can really help you. Okay, or how to apply this technique. So let's look at an example now. Okay. So in this example, we have a cantilever beam. So one end is a cantilever beam. Okay. So this is our point A. This is our point B, right? And then this is our built-in region at point B, right? And then we have a slope. Okay, we have a slope now. So we have a distributed load that look like this. Okay. So this is our distributed load. And our distributed load at one end, okay, it's not at 0, right? So over here is equal to 6,000 Newton per meter. And over the other side is 18,000 Newton per meter, all right? And that is spread over a distance from here to here. This distance now is equal to 6 meters, okay? So the next thing that we do now, to use the integration method, right? we need to find the function of the slope, right? And then we have to integrate twice. But before we go there, we need to write down our boundary condition. Okay, so this is where we write out our boundary condition now. So we're going to put below boundary